Hello everybody, this is a perspective you haven't seen before. This is my electronics workbench. As you might not know, I actually do a lot of electronics at home as a hobby. I've been mucking around for many years with this, and a bit of a thing I picked up from my dad. I really enjoy this stuff, and every now and then I get to and clean this area up and do a bit of work. Now, I've been following Morten for quite some time now on YouTube. He's a quite a interesting fellow in Denmark that does a lot of server engineering and server administration work. He loves his Lenovo servers, and he does a bit of electronics too, so sort of up the same alleyway as what I do and what I enjoy. So I've been supporting him on Patreon, and recently he offered to the Patreons early access to his kit that he's just created. Now, this is a desulfator kit for lead-acid batteries. This is the parcel he sent. So thank you, Morten, for this. We'll have a look and see how easy it is to build. Now, I have opened this up already. Obviously, I didn't have to tear this. It's given us a few little notes here, so we'll have a look at those first. There's our PCB. There we go, MyPlayHouse. It says here, "Hi there, dear supporter of MyPlayHouse YouTube channel. I thank you for supporting what I'm doing on YouTube, watching my videos, and now also supporting me by getting this desulfator kit. Thank you. Disclaimer, this might or might not work. It may not be dangerous. You're in control of your life and everything surrounding this desulfator kit. It is at your own free will and risk." That out of the way, I did a video putting this together, which is not made yet, so I've received this before he's released the video or even made the video. I've just started recording this just after he released actually the video showing how he made the PCB, and goes into the details of that. So we've got the contents list, so I won't go through that in detail. I'll bring that up a bit higher, hopefully that's legible. But we have a nice picture of all the parts and what they are and so forth. Resistor color coding, so that's handy. I actually don't remember this ever. I normally either meter the resistors or look them up. I'm a bit lazy like that, but we've got our schematic. And recommend to start with smallest components, tiny diode, D2 and resistors first. Keep mounting the smallest components you have left. Basic input. Okay, bits and pieces, the background of what it is, how it works. So it seems to be nice, signed by Morten. Thank you, Morten. Let's have a look. So this is made apparently by JLPCB. I've used them myself in the past for the odd little circuit board. I usually do my own prototyping and stuff on a VeroBoard, or some of you might call strip board. I've actually got some of it here. This stuff, you might be familiar with it. It's fairly cheap. It's good for doing DIY stuff, but it's nice to have a proper PCB. Now, we've got some basic parts. We've got inductors. Got a, what's this? IRF9Z34, I think that's a MOSFET. What is this? This is a NE555, so that's a timer. Got some capacitors. We have this fellow, that's a PPTC fuse. Electrolytic capacitors, power diode, some resistors, and our little Zener diode. I believe that's a Zener diode, I'm assuming. Oh no, it's just a standard diode. It's according to this, a 1N4148. So that's just a signal diode. That's a power diode, and we've got a little terminator, or screw terminal, sorry. So, simple enough. We'll just turn the iron on. I should have turned that on before I started this video. And we'll start on this from the beginning. D2. So this is clearly the top of the board. Where is D2? D2 is down here. We can see that it should be mounted in this direction. It's just standard spacing, so we'll just bend that direct and dump that in there. I was actually going to get my daughter to assemble this kit and do a bit of video on it, but she seems to be not that interested, so I guess I'll be building it. Clean my iron. I'm trying to do this. I've got the microphone between myself and the camera and stuff, so I'm trying to do this in a way that's sort of visible what I'm doing. But the camera I'm using is just an old phone. I don't actually have a decent camera yet, so I apologize if this is hard to see what I'm doing. But, well, we'll see how it comes out. I normally record stuff on screen, like actually on the PC, things I'm doing. So I don't need so much the camera, but in recent times I've been needing a decent camera. So there's a little D2 installed, trying to make sure that's visible to you. Actually, you get a better view of the board there now. Trying to get to focus. It's all a bit backwards, not used to working like this. There we go. Okay, next smallest, resistors. Now this fellow is brown, orange, black, violet, which according to our chart, actually I've read that backwards, hold on. Sorry. According to our chart, it's yellow, violet, black, orange. So yellow is 4, violet is 7, and orange is 3, so multiplies 3. So that'll be, orange is 3. Yeah, orange 3. So that'll be 470K. Simple enough. And according to this is R1. There we go, up the top there. The only thing I've got to say about this kit so far is it's nicely laid out. It's fairly easy to see where things go, and I like putting together basic kits. But the only comment I have for Morten, maybe it's only because it's the first ones he shipped out, is that perhaps the 555 IC should be put in a little bit of styrofoam or something just to protect those pins. That said, though, it did arrive here from Denmark to Australia without any issues. There's no pins on that. But I would suggest that as a change, that's one of the things he does. The other thing is these solder pads, while I'm fine with them, I've been soldering for many, many years now, while these solder pads for the resistors are technically large enough, I would actually recommend they be enlarged. The problem is, if this is put together wrong by a novice, someone that's learning, and they try to remove these parts using solder braid or a solder sucker, like a depult tool or something, solder pult, these pads are likely to lift off, and a novice will struggle to repair that or to get around that and get quite disappointed. So I recommend these pads be enlarged. So we'll cut that off. What's this fellow? This is brown, brown, black, black, brown. Have I read that the right way? These are 1% resistors. No, it's brown, black, black, brown, brown. So that's a 1K. So again, according to this is R4. Which is there. Seems like he changed the value. These early boards I can see is actually blacked out. R4 used to be a 22K and R3 was, or maybe not used to be, but there's an error in the silk screen that is corrected after the fact. So hopefully the final ones he's sending out has that corrected on them. Put that one in. I actually don't have any lead acid batteries at the moment that I want to run this on. I do have some, but they're currently in service, but I do want to pull them out soon to do a bit of maintenance on them. I have some replacement cells. It's in a UPS that I'm using. Next resistor, this fellow is brown, red, black. I believe that's red. Brown, red, black, red. That would be a 22K. And according to his sheet here, 22K goes in there. But I've actually not happy with how about that. We'll fix that. Okay, so that's the resistors done. Next component, probably, because we want to do the shortest components. The reason being is when you flip the board upside down, you can already see we're sort of moving around there because they're holding it off the thing. If we were to do the tall components like this MOSFET, I think it's a MOSFET. Let me just double check that. Yeah, it's a power MOSFET. If we were to put that in first, it would hold our board up, and putting any pressure on it or manipulating the board would fatigue these pins and snap the chip off or potentially damage it. The TO3, not TO3, can't think what it is right now, TO220 package. It would break those pins off that fatigue and break, or at least weaken, and we don't want that to happen. So the next component I would think is probably the 555 timer or the power diode. The time is probably a little bit shorter. To be honest, it's not too critical. But what I'm going to do is, Morten's given me the chip to go straight in the board, but invariably they're the most troublesome parts to remove when they fail. So I'm going to make a little change here. And I have some dip sockets. Whoop, if I don't drop any. And there's a little dip socket. We'll add that. This just allows us to pull the chip and replace it if something goes wrong. And these things are so cheap, it might as well chuck one in. The only downside to these is the connections over time. The push-in connections can fail. Might help if I straighten the pins. The other advantage to using it is that we don't actually end up heating the IC up. When we solder it, we're only going to heat that socket up instead. A little trick I find is just to bend the two corner pins over a touch to hold it in there. And make sure I've installed that socket the right way. Yes, I have. Not that it matters, you could plug the chip in backwards, but it's nicer if the pin 1 indicator is in the right place. Okay, so that socket's installed. Next component will be the power diode. That's clearly here. We can see the big diode on the marking on the silk screen, so we'll just fold him over there. The silk screen's excellent. It's very clear what goes where. There we go. Actually, what is this diode before we install it? Just curious. Can't quite read it. The markings aren't all there. This is a, according to the sheet, D1. It's a 4A power diode. So 600 volt, 4 amp. It won't be for the voltage rating, it'll be for the current rating. You can see he's got some nice thick traces on the board. Around here, again, I just bent those pins out a little bit to hold it flush to the board while I solder it. These will require a bit more heat because they're thicker pads and thicker wires. We're going to need some more solder too on these joints. Okay, that one done. That one done. If you like this kind of content, let me know. I do a fair bit of muck around with the electronics. I repair things and like to save cash wherever I can, so I pick up stuff that people are throwing out and repair them, try and get them going again. Just earlier today, actually, I repaired a little television. I'm going to do the capacitor next. This one here is a 47 microfarad, 25 volt. And according to the silk screen, it's not marked on the silk screen, so we're actually having to go to the reference. So the 47 mic is C1. C1 is down here. We can see the negative indicator on this side. The positive is also marked. Electrolytics can only go in one way. They tend to not like being reverse polarized. Usually ends up in a capacitor shooting its top off, bursting or whatever. Dave Jones of EUV has a few videos blowing capacitors if you want to see that. Some of his older videos are actually quite amusing to watch. You can see this one doesn't have a vent in the top. You probably find the larger one does. Yeah, you can see that little cross. I don't know if that's going to come out on the camera. So there's a little cross in the top of that. Sorry about the quality. Whereas this one, I can't really see that. It's too small for that camera. This one has no vent in the top. So this one would actually like just shoot the whole top off like a little bottle rocket, whereas this one would actually open and vent out. Depends on how aggressively it was misused. We'll do the next one, which is going to be C4 because it's the only other electrolytic. And we'll put him in the correct way. That's 100 microfarad, this one, 25 volt. Seems he has the wrong footprint for this particular part he's supplied. You can see here, we're actually going to bend those pins out if we put that in all the way. It's not going to sit flush. Sorry, but again, the camera's not really showing, the lighting's not great. Maybe if I adjust my lamp a little bit, hold on. Try and get a bit of a better angle on that. There we go. So you can see there, I could force it down and force it in. The issue with that is it can damage the capacitor because it's actually going to pull the leads funny. And inside here, where the capacitor is bonded to the metal, because these are like a roll of metal inside, it could damage that bond. So I'll just bring it to about there. And we'll put it in place there. Ideally, that footprint should be fixed or the correct capacitor should be provided for that footprint. I'll just double check I am putting in the right one. C1 is the 47. No, so hold on. C4, 100 UF. Yeah, so that's the one. Nice big traces on this one because it's clearly across the power for this MOSFET. The only issue, again, is those pads are tiny to solder to. So I'd suggest, again, the exposed surface there. Like over here, we've got some nice big exposed pads, but on that capacitor, again, there's little tiny pads. What next? Probably the other capacitors. These are non-polarized capacitors. Okay, so what's this fellow? This is 103. So the 103 is a 10 nanofarad, I believe. Yes, that's right. And we've got one of those goes at C4. I must be blind. Hold on. No, I've looked at the wrong line, sorry. We've got two of those at C5 and C6. C5 and C6. Again, we have the wrong footprint. This part is slightly wider than that on the board and it's not going to flush mount. It's all right, we'll just do the same thing again. It's a little bit of a shame. Because these pads are so small, I'm being very careful not to cut too close to the board when I cut those leads off, so that I don't pick up the trace. So that was C5, that's a 103, so that's a 102. It's a 103, this is the other one. This is also a 10 nanofarad. And this goes into C6, which is over here. Yes, it's even hard at the moment. The board's starting to shift. I might have to get out my helping hands in a minute. I think that took. Yep. Okay. I'll just grab my helping hands. Morten has his own version of these, so we don't need that. Pull that off. He's got some other clampy thing he uses. I think he did a video on that too, which was interesting as well. Okay, C2 is should be a 102. Yes, 1 nanofarad is C2. I like to place these when I install things so the print is readable without having to bend or move components. So I'm going to install them back to back. It doesn't matter direction on these, they're non-polarized. I could install it either way, but by putting it that way, if one of these parts sort of does something funny or fails, I've got to trace the circuit out for whatever reason, it's very easy to see without the schematic what that part is, without having to bend the parts so you can read what's on the side of them. Let's put that in there. Okay, so that's those two installed. Now we have this fellow. This is according to it's 2A473. That'll be a 47 nanofarad cap. That goes in C3. Where is C3? Well, look, R3. We missed one. What's R3? We're missing a part. R3 is a resistor. It's in the bag still. Look at that. I just noticed it. R3, we'll do it first, is a 1.8K resistor, which is right. Where are you going? Just saw it on the solder mask. And it's down in there. No big deal that that's a short one. We're putting it in late. We can get him still. I mean, you can install them in whatever order you want, really. There's no sort of tried and true way. But Morten's correct in recommending the shortest parts go in first, just to make your life a bit easier. Okay, C3. Where is C3 on this thing? Here he is. Again, this time the footprint's really wrong. This is C3 just here. This is far too skinny for that fellow. I do understand why they're wrong. I've had trouble myself because I only design the odd PCB here and there for the odd thing I want. Usually I build everything on prototyping board. And so when you actually go to use the design tools, you're never sure out of the millions of options it gives you as a novice which one is the right footprint for the parts you plan to use. Okay. All right, that's all the electrolytics done. This is the next one. This is the PTC. This is a thermal fuse, a poly switch. So what these do is if all of a sudden too much current's conducted, they've got like a polymer inside them that melts. And when it melts, the resistance goes through the roof. So it's like a fuse that blows, but as soon as it cools down again, it'll reset. So it's a good way to protect a circuit in a way that won't cost you anything if the part fails. Now, this has actually been designed to be mounted off the board. So while I don't like the way that this is done, so he's staggered the two holes for this one. I would have preferred them to be in alignment just because I'm a bit OCD, but what he's done's fine, so we'll just put that in. All right, and you can see there it's got some wiggly bits in the leads to prevent you pushing it in too far. You could, of course, straighten them and push it right in, but they normally do that, so it's got a bit of heat dissipation. I don't know if that's the case on a PTC, but that's there for a reason. It might even be just thermal stress to relieve stress or stop you damaging the epoxy on those legs if you try and force it in too far. Okay, we've got inductors and the terminal block. So we'll put in the block first. So now we've got some parts that are getting a bit tall. So we'll put that fellow in. Now I'm going to use the helping hands to hold it so we don't squish any of those parts. Wait for the part to heat up. And that copper trace. There we go. That just took. These ones take a bit more thermal energy to heat them up so that the solder will wet properly, because there's more thermal mass up inside this junction in here. It's got to heat up as well. Well, it's sucking the heat away from the join. They stick out a bit, so we'll nip them off too. And we have a couple of inductors. So this one here will be the 220 microhenry. Straighten him up a bit. Looks like it's unraveled a little bit in post-stitch, but that's fine. So before I assume L1 is that one, yep, 220. This time the holes for the inductors are quite oversized. We're going to have to put that in here. Now I want this to mount up flush. Actually, what I might do is, because I don't want this to over time be damaged, I've got I built some battery packs up a little while ago. I had to tear down and rebuild them again. So I've ended up with all these little strips of like hot glue. I've been saving them for jobs like this where I just use the hot air gun and we just warm that up. And we're just going to drop that little blob on there. We're doing this one. It doesn't look great, but what we can do is just warm that up again. It's my favourite way to use hot glue. All right. Got to straighten that leg up again. All right. And there we go. Oops. So now it's actually well and truly under the component. Got a little bit on the leg, it doesn't matter, it'll come off when we go to solder it, or I can pick it off now. And that'll keep that in place while it's soldered too. Hot glue does two things. It helps you solder it in, helps like hold the larger part in place, but also relieves the stress on these leads. So if this bumps around or whatever, it's no longer going to bend the lead under there. So we'll do the same for the other inductor, especially since there's a lot more mass in this. So if this bounces around or whatever, it could get damaged easier. So again, we'll just warm up a little bit. You could just use a hot glue gun, but it's a bit hard to run remnants through the hot glue gun. Done. Apply that. Stringy bits. Don't want stringy bits. It's alright, it's easy enough to clean them up too afterwards. install this inductor. Okay, now because of the copper has soaked the heat away from that hot glue, this is where the heat gun gets really handy. This is actually a hot air rework station, just a cheap one. If you're going to do electronics at home, even if you're not doing surface mount stuff, these things are so valuable, like for heat shrink and stuff like this. If I want to pull this apart again in the future, just to solder the pins and then warm it up and pull it out, I don't have to stress anything on the board. Okay, just holding that while it sets up. They're a little bit close, move that back. Okay, that inductor's in. That's a 1000 microhenry inductor. All right, that's still setting, but that's okay. So our last part to install is the power MOSFET. And this is going to go, you can see marked pin 1 on the left here, and you can see the double line there signifying the back of the MOSFET. So we install him. Now, that inductor is taller than my MOSFET. So what's going to happen is the MOSFET's going to fall out a little bit. What we can do is just pick one pin and solder it, then pick the board up, put a little bit of pressure on that and remelt the solder to make it sit flush, and then solder the other pins. That one's done. That's done. Okay, just clip the leads off. Make sure everything's right. Seems like a little bit of solder came through onto the other side. That's fine. And then we install the IC, which is the last part. Now, the pins are pretty straight on that. We should be able to just put it straight in, but the pins, when they sell these ICs, they have the pins pre-sprung. They're out a little bit. Not sure why they do that. Possibly for pick-and-place machines or something, but just fold them a little bit on the table to straighten them up. And we'll insert that with pin 1 to pin 1. Done. There we go. So that's our completed circuit. Now, like I said, I don't have any sealed lead acids on me right now I can test this with. But what we can do is we can apply some power to it and see what happens. Now, curiously, we only have the one connection on this. I assume that this is running in series with the power supply, with the battery. No, pin 1 is VCC, pin 2 is ground. Sorry, just bear with me a second. Desolder connected to 12-volt battery will, by making a magnetic field, collapse it again. And collapsing it again. Each time power spike battery. Okay, so this is normally connected across the battery. So not to a power supply. This should actually be connected to the battery terminal. So his schematic, unfortunately, is showing VCC. We bring that up here. VCC here. That normally means like the power supply, the power rail. It actually should be showing the battery indicator, which if I grab a pen, 1 second, should be find a working pen. This one should be right. It's going to work for me. Yep. battery indicator is normally like a stack of plates like this. So this would be, actually, I think I've done that backwards, but I think that's the negative and positive. But even still, normally a battery is shown this way. So this actually should be like that. These shouldn't be on here. So a minor correction is we should actually be drawing a battery on there. That'll clear that up. Peak voltage test point after that diode. All right, so what we can do, my only concern here is I've got a bench power supply, but I think this might be dangerous to power it up off the bench supply. It might damage the supply because it's expecting a battery. So what I might do is grab a standard diode, and we'll use the diode to protect the power supply. We'll energize this. Whoops. Okay. Now it seems that's come off. All right, so we're just going to use a diode. Might help if I had a screwdriver. 1 second. Went to Europe about 7 years ago and picked up this at Lidl. We have a similar store here called Aldi, but Lidl's like very similar over there to Aldi. And it's a brilliant little set. I think I only paid like €3 or €4 for it at the time. It didn't come with an actual driver, but I've got a handy one here from another set. I do actually have a set of screwdrivers, but I thought I'd just show you this one because I think it's pretty neat. So we've got on here, another thing that Morten should do is also label on the silk screen which one, he has actually, it's just hard to see it. There's a positive there and a negative there. So it's hard to see that. They should be part of the silk screen, not the copper layer. So that's another minor correction. We'll put that in there. Don't need to tighten that up tons. I won't use the handle, get too much torque on it and damage it. We'll just get one of these scraps. Another heavier ones. And we'll just use that so I can put my alligator lead onto it. So before I power it up, we should do what you should always do with these things is check it for any shorts. I do have a bench meter here, like a proper bench meter, but you guys can't see that. So I'll pull this fellow out. This is one of Dave Jones' meters. I actually have his 121 GW meter as well he sent me. But it's currently doing duty in the roof where I'm working on my solar system. So we'll use this one. So we want to do a diode test. Keep going, this one. No, we don't. We want, sorry, ohms test. There we go. We look for a short. Nothing. And that was the diode turning on. So we'll have a short until the diode switches, and now the diode's on. If we go the other way, same deal. Or a capacitor's charge. I think there's a diode across that though. Not sure. Doesn't really matter. All that matters is we don't have a short circuit there. So we'll get our negative lead. We'll also get another alligator lead. Just for convenience, connect this to the multimeter, to its negative probe. Just so I can probe around on the board without having to handle two probes. We'll turn our bench supply on. We're going to set it to 12 volt. We'll limit our current This is a constant current power supply that my dad built something like 30 years ago. I will limit the current to 100 milliamp. And yeah, apply power, see what happens. Hold on, we'll actually verify where that test point is. On the data sheet, he's actually marked the test points after D2, between D2 and C6. So that's the diode, that's the little signal diode, which is, it's hiding now, can't see it. It's over here, D2 and C6. So the test point is on this corner just here. All right, so let's power this up. Let's hope it doesn't damage my supply. Already showing overcurrent. So we've gone into constant current mode. We have wired it up, positive, negative, yep. And we're seeing, set that to voltage. Okay, seeing just about nothing. We need to bring the current up a bit, I believe. I'm at an amp. It's dissipating an amp of power. I've disconnected power because that doesn't seem right. Can't feel if anything's getting hot. Oh, hold on. I forgot to turn the output on the power supply. All right, we'll go back to 100 milliamp. There we go. Output's turned on. All right, I can hear it. I can hear a whine coming from it. It's clearly oscillating. We're seeing 71 volts. So it's clearly working. I do have an oscilloscope, but you guys can't actually see it. What I might do, I'm going to probe it anyway. I need a probe first for that. Cleaned up and disconnected them all. I should have left one on. Oh, sorry, bumping the camera. Okay, turn the oscilloscope on. What we're going to do is hook onto our negative. And we're going to hook onto that test point. Just waiting for the oscilloscope to start up. Okay, we definitely have... We have a sawtooth oscillation happening. Yeah, let me grab the camera. We'll move this so you can see. Then we'll probably end the video. So I just knocked my lamp. Might turn this lamp off too so you can actually see that, getting a lot of glare. Okay, so that's the test point on that circuit. So it's clearly working. Oh, we just lost our tracking. We need to move the trigger. There we go. So well done, Morten. Your circuit works. Just a few bits and pieces to fix on it, like the footprint, a few comments on that. But yeah, it was easy enough to build. I think pretty much anyone could build that, provided a few things are changed, like the tiny little pads and stuff. So I think that'll end this video, and thanks for watching. If you guys like what I do, don't forget to subscribe and like this video. It does help. I also do have a Patreon. The details will be down the bottom in the description as well. I do a lot of work on various things, including the Linux kernel, and if you haven't seen the Looking Glass project, a lot of server stuff, virtualization stuff. And if you want to see me build more stuff, just say so in the comments, or if you've got anything you want me to muck around with, or I'd be happy to receive it. Just send me a direct message and I'll get in touch. Just one more thing. I just thought I'd quickly connect the probe onto the output over here too. And I've just changed the scope settings. You can see that what it feeds back into the battery. This is why I put the diode in here. I don't want this to feed back into the power supply. But you can see there we're at 50 volts per division on the vertical. So we're there at, what's that, about 75 volts, which is what we saw on the test point. We're at 500 nanoseconds on the horizontal scale. So that's 1,000, 2,000. So it's a 2,000 nanosecond pulse it's providing to the battery. And that's happening at, what are we? Oh, there's 20 volts per division. Less than 15 kilohertz. So this is fairly slow. There we go. So it's 2.67 kilohertz this circuit runs at. So there you go. Well done, Morten. Works beautifully.